area between two curves, r equals f of theta and r equals g of theta. So when we calculate this one here, so let me draw a little picture. All right, so I've got this function f. So f function, and then I've got a function g. All right, and so what I want to do is I want to find the area from theta equal to A to theta equal to C here. And now, why did I skip B? Well, there's an important thing that's going on here. These two functions are flipping around. This curve now is the G, and this curve is the F. As you can see there, it might help if I change the color. Okay. All right, so maybe that'll help. Okay, and so what we have to account for, if I'm going to find this area here, this red shaded area here, all right, then what I need to do is I need to do the outside minus the inside. Okay, so it's just like whenever we had two functions here and here, and this was f and g, and I wanted to find the area from A to B, and I wanted to get this area here. You do the top minus the bottom, right? So it's the same thing here. I do the outside function, outside minus the inside. Okay, but the problem is the outside becomes the inside here, and the inside becomes the outside here. So you got to be careful what's inside, what you're calling inside, what you're calling outside. So because there's that swap going on there, we have to break up the integral where they intersect, and so you got to figure out what theta gives you that intersecting value. Okay, so you have integral 1 and then integral 2 going on there. Okay, so the formula for area is equal to 1/2 integral A to B, and then it's the outside squared minus the inside squared d theta. Okay, so the outside function minus the inside function. Okay, and now for this particular problem, the first one integrates from A to B. Okay, if I integrate from A to B, and I have 1/2 the outside squared. So what's outside here? The outside one is this f of x, or f of theta squared, minus the inside. Well, what's inside? The g of theta is on the inside for that particular one. D theta. And then plus 1/2 integral a to b. I'm sorry, not a to b. Where do we start summing? We start summing at b. Okay, so we start at b and we sum all the way to c. Okay, so from b to c of, well, what's outside? Now the outside happens to be g. G of theta squared minus the inside here is f of theta squared d theta. Okay. So that would be how you would solve that particular one. So let's do an example where I show you this in practice. So find the area of the region that lies inside r equals 4 sine theta and outside r equal to 2. Okay? So let's see if we can actually graph this, because this is kind of a foreign thing just to think about. What is this telling me? R equal to, so a radius is always equal to 2, okay? A radius always equal to 2, no matter what theta is. Could be 0, could be pi, could be 7 pi over, 6, whatever, right? Anything negative. Well, no matter what theta is, r is equal to 2. So that means I go out a distance 1, 2 from my center, and I put a dot. And in any direction I go, I'm always 2 away. Okay? So what does that remind you of? Should remind you of a circle, right? So that is a circle. R equal to 2 is what that graph is right there. Now this next one here, r equal to sine 4 sine theta. This one may be a little bit harder to see, okay? But if you have trouble seeing what this is, then just plug in theta values. When theta equals 0, what does it get you? 4 sine 0. So 4 sine of 0 is 0. So I'm at 0 for 0. Whenever theta is equal to pi over 6, what does that get me? 4 times sine of pi over 6. Pi over 6 is a half, so 4 times a half, that's 2. Okay, so it pops me up to be 2 away. Well, guess what? If I'm 2 away, that means I'm actually crossing the circle, doesn't it? Okay. So you see there that if you're 2 away, then you are exactly crossing that. You're crossing that circle. So where are you crossing the circle at? At theta equals pi over 6. So I kind of got lucky on that one. All right, now this thing keeps going out. Really probably not the best at drawing this. So at theta equal to pi over 6. All right, and when theta equals pi over 2, what do I get? I get 4 times 1, so that gets me 4. So I'm going to go up. I need to move this a little bit, otherwise I'm not going to get this to fit. All right, so 1, 2, 3, 4. Okay. So kind of like that. So I go up to 4 there, and then I'm going to work my way back down and come down through there. So that's r equals 4 sine of theta. Okay? r equals 4 sine of theta. Now, what I want to do is I want to figure out what is the area that lies inside this region. So inside this region is here. Okay. And then outside that region, so that outside that region is everything out here. So where does this overlap at? Well, it actually overlaps in the middle here. So this is the region that I'm trying to find the area of. That's inside the blue circle, but outside the red circle. All right? So I'm trying to find that little purple area. Okay? So how do I do that? Well, I need to know the angle at which they intersect. So they intersect here, and they intersect here. Now, we accidentally found that angle, but how would you find it otherwise? Just like you would if you had two graphs, two equations in college algebra or whatever, you'd set the parabola like x squared equal to, the, I don't know, y equals 2x plus 1 or whatever, right? You'd set these two equations equal to each other to find where they cross. You do the same thing here. I have r equals 4 sine theta, and I have r equals 2. So I'm going to say 2 equals 4 sine theta, divide by 4 on both sides. I get 1/2 equals the sine of theta. Well, what angle produces a sine of 1/2? Well, I know theta is pi over 6. Okay, sine of pi over 6 gets you 1/2. That's one of them. The other one is, well, if I use reference angles, I know that this goes all the way over as pi. But if I go up a pi over 6, because those are symmetric, right? So all I have to do is pi minus pi over 6, and I get 5 pi over 6. So 5 pi over 6 is the other angle. So theta equals 5 pi over 6. So I'm going to integrate from pi over 6 to 5 pi over 6. And I'm going to sum all the way around. I'm going to sum all those wedges all the way around from pi over 6 to 5 pi over 6. And I do the outside minus the inside, squaring each piece. Okay? So let's do that. So the area is equal to the integral. So it's 1/2 the integral from pi over 6 to 5 pi over 6 of the outside squared, which is 4 sine theta squared, minus the inside squared, which is just 2 squared, d theta. And so if I do this, I get 1/2 integral pi over 6 to 5 pi over 6 of 16 sine squared theta minus 4 d theta. I'm going to factor a 4 out. I'm trying to make this as easy as possible. So 4 over 2 integral pi over 6 to 5 pi over 6. Okay. And that gives me 4 sine squared theta minus 1 d theta. Now 4 over 2, that reduces to just 2. So now I'm going to integrate this. Excuse me. So I'm going to do 2. Oh, wait. I think I figured out that I can't multiply those at first. So I'm just going to do the integral first. So pi divided by 6. And then 5 pi divided by 6. And now I'm going to do 4 sine x, close parentheses, and I actually want to do square there, but I want to put another parentheses. Oh man. There we go. Okay. And then minus, oh, not plus, minus 1. Hopefully that will work. And then hit enter. Okay. And I'm going to multiply by 2. Good. So I get roughly 7.65289. Now, if you did this and you got the exact answer and you worked through this, which you could definitely do with your reduction identity, break this into 2 integrals and you can do this pretty fast, okay? And you would get 4 pi over 3 plus 2 square root 3. So that would be the exact answer, but this is good enough if you show me, you show me the work to get from here to this point right here. That's going to be good enough, okay? But you could integrate this by hand if you wanted to. It's one of those that would actually end up working for you. All right, so hopefully that kind of shows you how you might try to do these types of problems where you have 2 and you're trying to find the area between the curves. Part of it is figuring out what theta value those 2 different curves intersect at. And I believe there is a way to graph these on your calculator. Your 84 might be a little bit easier. All you have to do is Google how to graph polar graphs on TI-84 calculator. And if you do that in YouTube, you'll probably get 50 videos showing you how to do that. With mine, they have y equals, so I'm not quite sure if I'm set up where I can do that. Okay, well, hopefully this video was helpful.